Okay, well, thank you. Let's see, where are we? First, I need my laptop to show up. I see it here.
You have to press the button.
It is, which button? Oh, okay.
It's not there, that's the one. And that'll work about half the time, I think. Yeah.
Okay. Now we're rolling. Though that's not the starting point. This is a good place to start in terms of help you click your way to the tutorial. So this is the schedule. You know how to get to here. And then just click on the vector tools. Again, just to find your way into the main page. And now that you're all here, or at least you can look at the screen, I'll step back and say hi. My name is Emilio Mayorga. I'm at the Applied Physics Lab here at the University of Washington, same place where Anthony spends half his time, and same place as Don also. I am originally a river biogeochemist. I'd like to think I still am, but these days I do more data management and transformations and data systems, for better or for worse. I'm jealous of David Buttman, who gets to do biogeochemistry and go to the field. So we'll be talking about vector tools, preamble, well, one bit of preamble. Hopefully you all have what's listed here. You have Conda, you have access to Jupyter Hub, you know what Python is. Quick show of hands. How many of you have either taken a GIS class, even if you never used it, or done enough GIS that you open ArcGIS on a monthly basis, right? Show of hands. All right, that's about 2/3. Okay. Sorry, I'll be wasting some of your time, but we need to be on the same page, so you can multitask if you want. Hopefully you don't take a look at these prerequisites, but hopefully you won't need anything from it. We have instructions here in case you want to go home and install a local Conda environment to do this same thing, or do it tonight, I guess, because it's so much fun that you want to do it twice. There's links also to the Jupyter Hub tutorial and the Conda tutorial and so on. I'm not sure if anyone used this template yesterday, this software carpentry template. So a little orientation if you want to navigate now or later on. All the episodes, so these things that are listed here are called episodes. You can access them wherever you are through this listing, the episodes. And I also took advantage of this reference link to provide some resources, some links that you may find useful in the future, especially if you speak French. There's a few links in there that are good and just happen to be in French. Okay, so we are done with that. Oh, another thing, this you don't have to really care about this because Jupyter Hub and the Conda environment will take care of this. But FYI, I guess I'll click on this. We'll be running the notebooks on Python 3.6, but we have tested, or at least I trust Don tested it when he told me he did, on 2.7. I don't remember if people, well, I got in late yesterday, so I don't know how much people cover the issue of Python 3 versus 2.7, and that divide in the community that Python 3, so this might as well, Don is saying now, so might as well touch on it a little bit because it's an issue you'll run into for at least a couple of years. Python 3 has been around for quite some time, but it's taken a while for libraries to get there. They're all essentially there, at least the core libraries are there, but we're all slow. Some of us are still on 2.7, certainly me, and a large section of the community. So as you interact with others and code from others, that's a very important divide that you need to be aware of. Again, all the work that I do is pretty much on 2.7. I'm not proud of it, but it is. But this tutorial is guaranteed to work on both, according to Don. Okay, another caveat, I guess, that or disclaimer that I'm not here to cover GUIs, to cover ArcGIS or QGIS for open source. We're here to start out with fundamental concepts on vector data, and then present some cool and useful programming tools, Python tools for, well, programming sounds bad, I guess, but interactive coding tools that are provide a lot of power and also serve you as a launching point for wider capabilities in Python. So no graphical user interface will be harmed in the making of this tutorial. Okay, vector. If you're coming from the earth sciences, and most of you are, and if you don't have a GIS background in particular, I say vector, and you will imagine, especially if you're a meteorologist, you will imagine, oh, winds. Vector that points in that way. No, sorry. GIS is has a different lingo. If you have that, for the 2/3 of you that come from GIS or have GIS, you know what I'm talking about. These are not fields of arrows indicating direction and magnitude. It refers to discrete geometric entities like lines, points, or polygons, and other more complex objects, or primitives, or lots of synonyms, shapes, features, that typically represent distinct things on Earth, on land surface. Well, if you're taking a GIS class, typically they'll use the land surface, but it could be on the bottom of the sea, or it could be on Mars. It's a way to represent areas. And typically there are some features on Earth that really are distinct. They're kind of rare, but you may really have a boundary. But typically these are simplified representations of the real world. Vegetation, for example, rarely has sharp boundaries. Plants go back and forth. Rivers are often a line, but go to any river, and it's typically not a line. It's a little bit wider, and it even varies depending on the season. So very often, vector data is used either to represent simplifications that are appropriate for what you are for your application, or in the case of human-built environments, it might actually represent reality, like the footprint of a building. But anyway, so unlike raster data that we'll get to, typically we're dealing with simplified representations. And typically, we don't use vector data to represent continuously varying fields. Typically, you would use raster. But boundaries get fuzzy, depending on what you're doing and where you're coming from. So again, for those of you who have a GIS background, bear with me. I'm going to go back to the beginning and introduce a common language for referring to geometric objects, the types of objects, and geometry and attributes, because I do feel that language is very useful, not just so that you go away with really cool and basic knowledge, but because that language is reused in the Python tools we'll be seeing over and over. So it serves as a very helpful grounding for understanding how to use these different tools. So simple features. The Open Geospatial Consortium define the standardized set of geometric objects and the functions or operators that have been widely adopted, certainly in open source software, but I think also in commercial geospatial software. And this represents two-dimensional planar geometric objects, although there are now other more complex objects that I won't touch on. And here we'll focus on the most basic and common types, and really the vector subject you'll run into most of the time for at least the next couple of years. And they're made up of 3 basic single entity geometric types and their associated collections of those entities. So those 3 basic types are points, or a point, a line, or a polygon. So that means 1 point, 1 line, and 1 polygon. The homogeneous entity collections are multi-point, so in other words, the same 3 that we just saw, but multi-versions of those, multi-point, multi-line, and multi-polygon. And these are illustrated, or at least the primitives are illustrated below. So when would we use single versions of the entities versus multiple collections? They're not there aren't any really hard and fast rules or that you must always use one or the other. It really depends on what you intend to do with the data. What is your most common use? So one example for polygons is states. The state of Washington, really just about any state except maybe Utah or Colorado, tend to have complicated geometries. And often it's not just one polygon. There may be another piece off to the side, or there may be a lake in the middle that in some cases might be cut out. But if we take Washington as a better example, besides you're here, we have lots of islands. So in reality, if you go to the single entity representations, you could choose to represent Washington as however many, well, the mainland and however many individual islands we have. And there are good reasons for doing that in some circumstances. For example, if you're going to have attributes that represent the name of each of those pieces, then you have to do that. You have no choice. But if you have, because otherwise you can't attach the attribute to the individual piece. But if you're going to have a data set, for example, of states, where each unit, for your purposes, each unit is a state, then it's more convenient for visualization, etc., to have Washington be a single multi-polygon that includes all the little polygons. So again, it just depends on applications, but you will encounter both as you download data from different places. So you have to be aware of it, and you have to be aware of conversions, issues, etc. It's worth noting that there is another simple feature type called the geometry collection. Basically, it's any mix of all of the above. I won't get into it because it can get to be a mess really quickly. It's also very handy if you know what you're doing, but we won't touch it today. So expanding on OGC simple features lingo, a feature refers to the combination of a spatial entity, so the geometry, any of those geometries we just covered, plus its associated attributes, like, for example, in the case of states, US states, it could be a name, it could be a category, like, is it coastal? Yes. Or any other property, like population density. So one feature is one geometry type plus its set of attributes, and a collection of features, like all 50 states in one shapefile, would be a feature collection. Again, sorry for the emphasis on lingo and terminology, but this will come in handy later on, I swear. Most real-world GIS vector data sets are really feature collections. You will rarely encounter a data set that has one feature, except as an intermediate step. Well, you can read the terminology hell note on your own, but it can get complicated. Standards, people who write standards are prone to, or the process leads to complex language sometimes. So we've talked about objects, the geospatial objects and the attributes and features, etc. But they're also what you do in GIS or with geospatial vector data. It's not just being able to represent data, but to do something with it other than just viewing it. And that's a set of operations that you can use to apply an individual object or across objects. So in other words, relationships between these objects. This include, I'm not going to be comprehensive at all here, but just to give you some common examples, they include buffering, dissolving, convex hull, touch, intersection, union, and others. And you're seeing here some examples of those in a graphical way. And the execution of these operations is at the heart of vector GIS, together with the representation of those objects. Again, we won't cover this in substantial detail or in any comprehensive way. We'll just illustrate some of those to give you enough of the especially GeoPandas capability so that you can then run on your own after this. Okay, in addition, at least those of you who have GIS background, you know about projections, and hopefully most of you know that the Earth is not flat, it's not even a sphere, it's not even a perfect ellipsoid. There are projections are necessary, and there's an abundance of projections, literally thousands, depending on the application, the region of the world, what you want to emphasize. Latitude and longitude, or what you get from GPS and its corresponding reference system, are very handy and can represent a point very accurately, although geophysicists might disagree on what accuracy is, I guess, or the level of accuracy. Transformations can be challenging if you're doing them at a low level, or reprojections. So typically, if you want to calculate area in useful units like square kilometers, typically you would reproject from geographic coordinates or lat and long into something more useful, or projected coordinate reference system, or something on a Cartesian plane. Some of us work at global scales, and at global scales, you almost always work on lat-long projections because it's so convenient. Those of you who work on subglobal, continental to local scales, depending on your context, you may find sticking to lat-long useful, or you may find that there's that favorite projection that you stick to. But anyways, the ability to go back and forth between projections is really handy, and we'll get to that. Okay, so enough background. Well, not enough background. There's more background. Any questions, comments before? What's next? Am I going too fast? Oh, my apologies. I hadn't had any coffee, and Anthony brought it, but I hadn't had a sip. So things will get better from here. We'll touch on very briefly on, so we'll start getting more concrete from sort of abstract concepts and language into more specifics of techie things. So covering some standards for encoding of this geometry and data, there are standards that to define how to encode these geometries and features. And I'm emphasizing standards to distinguish from something like any binary format that may be out there that you may like. Let's say you use, I don't use ArcGIS these days, but let's say any software that you use that happens to have its own binary proprietary format, it may be that it's a beautiful format, it's extremely efficient, and if you use only that software, it works great. You never have a reason to complain because all your friends use it, you can pass it around, your favorite software uses it, it's highly efficient, so who cares that it's proprietary and binary? But that's not why we're here. We're here to talk about open data and the ability to go back and forth across tools, and that's where standards come into play. Now you could define, you as some future MacArthur fellow could define a wonderful data encoding, and you can persuade all your friends that it's wonderful, and you develop tools and your friends use it, but that won't get you to communicate with the rest of the world. So that's where standards come in, both highly formal standards as well as community standards that have been widely adopted. Sometimes they're not fully ideal, or they may not be the most highly performant things, but they serve that communication purpose across people and across tools and across computers. So I'm going to be emphasizing that, and in terms of encoding geometry, a number of widely adopted standards exist from the Open Geospatial Consortium, or ISO, especially the well-known text and well-known binary and OGC geographical markup language, or GML, and GeoJSON, which is based on JSON. And GML, I wanted to mention GML in this context. It is pretty complex XML. I'm not going to get into it very much. I may touch it indirectly. I also won't touch on well-known binary very much, but it's good to be aware of it. In this tutorial, I'll focus mainly on well-known text and GeoJSON, partly because it's human readable, but partly because they have taken on a great role as glue between software to pass data around, basically. So well-known text encoding represents geometric entities in a fairly intuitive way, a fairly readable way. You can see some examples here, and based on the language that I introduced a little bit earlier, this should be pretty obvious. That's point, multi-point, and the only thing to be aware of, but you don't really have to memorize this, so it's the order of coordinates, that in this case is x, y. GeoJSON arose as a community convention from that leveraged the predominance of JSON, especially on the web, but not just the web. It also arose because, part of the beauty of JSON is that it maps really nicely and in a very simple and efficient way into programming constructs. In JavaScript, if you're doing web development, but more to the point here, into Python dictionaries. So GeoJSON sort of leverages that ease. It's not the most efficient. It's pure text, so it's not extremely efficient for compactness of storage. But it's and it has other limitations, but it's a terrific representation of geospatial data for interoperability and web stuff. I have added some resources in there that you can click on at your leisure, either this week or later, to say more about GeoJSON, to show you some tools that allow you to do cool things online directly. So for example, because it's so predominant and easy and web-friendly, if you drop any GeoJSON file on your GitHub repo, GitHub will render it. Just click on the file and it'll open a simple map with a simple background that if it has points, it's clickable. So it's just really, there are a lot of really convenient things to it. Because of that convenience and because it became widely used, even as several years ago, a few years ago, a community convention arose, especially among open source tools, but it was also embraced by ArcGIS scripting for a common method to be defined on different tools to pass data around. So you have a Python package that you install here that does X, Y, and Z things, and another one that specializes on these things. And they may represent data differently internally, and you shouldn't have to care about how they represent data internally. But if you want to pass data around so that you leverage the advantages of this tool from this tool, if you don't have a common way of communicating, you'll be doing a lot of idiosyncratic conversions. So what this standard or this convention did is geo interface method is that if everyone, it defined what it would be so that every tool developer could implement it, and every one of these tools could include this function that basically transform its internal data into GeoJSON-like representation. And that allows for, again, fairly seamless transfer of data between tools. And I'll show that in action in a couple of instances. And here's an example of GeoJSON. You don't have to memorize it. The main thing is that there's a type. In this case, it's feature collection, and then a list of features, and geometry, and so on. So I've been talking about encodings and not the things most of you who do GIS really use on a regular basis, which would be formats, file formats, shape files, and so on. Obviously, they are fundamental. Hopefully, most of you, I don't know if they still, I assume they still teach shapefiles, even in an ArcGIS class. Shapefiles are like democracy, I guess. They are, the worst possible format except for all the others. I guess it depends on your goals. But they have become, for better or for worse, the lowest common denominator for data exchange across all systems. It's not an open source format, but for all practical purposes, it's well defined. It's an awful format, but it's here to stay, unfortunately, forever. There's GeoPackage is emerging as a possible replacement. It's based on the file-based SQLite database, relational database, and then others, S3 file geodatabase, which is semi-open, and so on. Some of you may be exposed to geospatial data storage on relational databases, especially, hopefully, post-GIS. But if you are an ArcGIS world, you may be doing SQL Server, spatial component, or Oracle spatial, and so on. And then there are packages to deal with files, OGR, Fiona, which we'll get into indirectly, PyShape, and so on. And then there are libraries also for projections and coordinate systems. And I won't try to cover everything you need to know, or even all the basics about projections. I think someone, what is it, Randy maybe, covering projections. But still, I'll be touching on it just to illustrate capabilities from GeoPandas and these related tools. Okay, you can use this to navigate. Okay, finally get into real things, or a real notebook. This episode, GeoPandas Introduction, what you see here is basically an export and slight reformatting of a notebook. So from now on, it's just notebooks. No more static text and me just blabbering without running code. you'll see a link below. You don't have to click on it, but it's for future reference. That points to the location of the notebook itself. So later on, when the Jupyter Hub server has disappeared, you will always have this static reference and the link and the pointer to the notebook that you can run locally or whatever you want. I actually won't be referring to this directly because I want to run this notebook live. But you can feel free to open it or see one of the notebooks statically or just run the notebook together with me. So I'm going to jump here to Jupyter Hub. And like I said, I actually did the same thing you were doing. I did a get pull to update my account on Jupyter Hub. So that's what you should be seeing right now when you start Jupyter Hub. There's the tutorial contents. You click on it, and there's 3 of us, I guess. There are 3 tutorials. So click on Vector. And that's what you'll see. We'll click on Notebooks, and then click on. Actually, I guess I need to set before you click on the notebook. I imagine someone can.
You can change mirror once you open it.
Oh, okay. Thank you. So I'll click on the notebook, and then I'll change to the environment we need. There we go.
Kernel.
Kernel. Okay.
And then change the name.
So change to vector env. And I will do a little bit of let's see, toggle, just to give us more real estate. Oh, and I remember, is that font size useful? I'm not used to this presentation style, people having a big screen next to them. Should I make it a little bigger, or is that good enough? Okay. I don't see anyone complaining loudly.
A little bigger.
Are we good? I missed that. Sorry.
I was just a Jupyter question. What kernel does it snap?
Okay. As long as you know that you open the notebook and you change to vector env. GeoPandas. It brings to GeoPandas is built on Pandas. I guess this sort of the first full-blown Python intro that you're seeing. So I guess raise your hands if you have used Python and have used Pandas. Just good. That's about less than half, I would say, slightly less than half. How many of you have not used Pandas in Python but are R users? Okay, so I think we're close to about half of you. How many of you are familiar with relational databases? Very familiar. Okay, so I think we've got about half to 2/3 of you covered. I'll start with Pandas, even though it's not mentioned in the notebook. Pandas, well, it does many things. It's become really widespread and widely adopted, and huge community supporting it, supporting the development. At its core, one of the things it did that was missing in Python and that Python suffered from our envy is this data structure called a data frame. I don't remember what it's called in R, but it's essentially like a relational table. With all the advantages of having the ability to have columns and column names and rows and row labels in some cases and good indices, and then defining operations on those things that are useful. Again, this data frame should be very obvious to you if you use relational databases regularly or if you use R. I don't know what else to say, I guess, but if you have trouble following anything because you don't quite get Pandas, raise your hands as we get along. GeoPandas came along to build on the success of Pandas. So Pandas is purely about individual values and attributes. Now Pandas has other objects, series, data frames, and panels, but I won't get into them very much, especially not panels. So GeoPandas came along to leverage all the goodness in Pandas and add spatial component. And this was very natural to those of us who are GIS geeks, because essentially a GIS data set is like a data frame with a geospatial column, or a geospatial data, I guess, in addition to the attributes. So that's the first thing it does. It defines the data object, if you will, that is just like data frames or just like a relational database with the ability to have a geometric type column. And it leverages a lot of open source core libraries. One of them is called Shapely, and it provides the machinery to define these object types. But it also defines spatial operations. So GeoPandas, just like Pandas, in addition to defining the ability to create these objects, it also folds in a lot of these core vector geospatial capabilities and operators that I mentioned before. The ability to do projections, the ability to handle feature collections, and just like Pandas, let's say sum two columns if they're integers or numbers in a very simple syntax, like a plus b, sort of, to define a new column, as opposed to what most other geospatial libraries had forced you to do in the past, which is iterate. Have a for loop to iterate over every single row, which gets old and tedious very quickly. And it turns into code that is not just tedious to write, but hard to read, ultimately. So GeoPandas made geospatial operations easier, and it leveraged really a huge amount of core open source geospatial libraries into a package that is kind of an umbrella almost of capabilities. And so last statement there, just like Pandas, it also has a very convenient fine-tuned plotting method that leverages matplotlib that makes it easy to do simple plots. When your goal at that instant is data exploration rather than creating that 6 feet by 6 feet cartographic beauty. And it also includes components that to handle serialization or file reading and writing in multiple formats. Again, leveraging geospatial libraries. Like Shapely, the spatial types are limited to the ones I introduced. There's single entities, there's 3 single entities and 3 multi-types. And one thing to keep in mind is that GeoPandas can store a coordinate reference system as metadata, if you will, but it doesn't handle transformations automatically. You kind of have to know what you're doing, or you have to pre-convert. It gives you easy tools for pre-conversion, but you can't take a GeoPandas Geo Data Frame in one projection and another one in a different projection and sort of overlay them. You have to consciously convert from one projection to another before you apply the operation. And be aware that GeoPandas is still somewhat young. A release was issued just 2 weeks ago, 0.3, 0.4, I forget. So it's developing rapidly, but expect a few kinks to still be there. So what are the, at least according to me, when is GeoPandas optimal? I would say definitely for exploratory data analysis. It just simplifies so many steps, especially when you're in a Jupyter notebook. Also for highly compact and readable code that you want to get back to later. So it may be, let's assume that there is a performance hit, and I'm not really sure whether there is. I haven't done any benchmark comparisons or read about them, but the compactness and the intuitiveness of the code is a goal in and of itself, and you'll value it when you get back to it later. And it improves reproducibility. And again, if you're comfortable with Pandas, or if you come from an R background, GeoPandas will be very natural to you. When would it not be the right tool? Definitely if you're doing polished map creation for the 6 by 6 foot cartographic, highly detailed beauty. I mean, GeoPandas might be an intermediate, or you might use this for data storage, but its plotting tools are not, they're really a convenience. They're not for that final, extremely detailed cartographic control. I'm not quite sure about performance. It's improving. There are a couple of things in the works in GeoPandas that are going to make it faster. Some in the short term, others in the longer term, including potentially Dask serialization. And Anthony will talk about Dask a little bit later in his XArray presentation. Okay, finally we can get to code. I will say first that a caveat that matplotlib, and if you haven't heard about matplotlib, if you don't use Python a lot, just about everything you will encounter that involves plotting in Python in the earth sciences is based on matplotlib. If you come from a MATLAB background, matplotlib is mostly familiar to you, or will be. There was a major version released semi-recently, I don't know exactly when it happened, and that was version 2. I can't tell you right now what the main differences are, but there were some significant styling differences. So defaults were changed quite a bit. For some weird reasons that Don and I don't understand, when we were creating the vector environment yesterday, matplotlib defaulted to 1.5. So 1.5 is still supported. It's the last one in the 1 series. So totally good. But the defaults will probably be different than if you use 2.0. There's a chance that if you do this again in a week, there's a chance, because you'll be recreating the environment live, there is a chance that you will actually be getting matplotlib 2.0. And if that happens, everything will work here. But the plots that you will get, be it on Jupyter Hub or I guess not on Jupyter Hub because the environment is fixed there, but in your local computer, the styling of the plots will probably be somewhat different. The colors, the default sizes, and so on. So just be aware of that. And be aware of that distinction as we get into the other tutorials that may be relying on matplotlib too. So anyways, here's the libraries that we load. I will mention this part here that this statement, well, I guess I should be running this, I forgot. So I do want this to be live, and that's totally live, that annoying message. And the next step tells you the versions of these core libraries, just so that when you look back at this and you compare it to your local installation, you can be aware of what versions we were using, since versions keep improving and changes are introduced. Okay. So I will start small and build up complexity. I'll start with Geo Series, which is the data structure in GeoPandas, just like the Pandas series, that enables you to encode, to store a geometry objects without the features. So it's the building block for everything else in GeoPandas. I guess I'll read it. A Geo Series is made up of an index and a GeoPandas geometry data type. It borrows directly from the shapely geometry object, and we'll reuse that information later, and inherits everything that shapely geometry objects can do, including methods and properties. Just like the discussion the presentation of the geometric objects that I showed, it includes those 6 core geometry types. Both single entities and homogeneous ones. So a Geo Series, you can view it as a list of geometry objects and their associated indices. Be aware that, especially if you're thinking about the analog of a shapefile, I don't really know about if this is possible in an S3 file geodatabase, for example, but certainly in a shapefile, you will always have shapefiles are of a single geometry type. It's either a point shapefile or a multi-point or a polygon, but it's never both. You can't have a point and a polygon in a single shapefile. So be aware, a Geo Series and Geo Data Frames, for better or for worse, allow you to have a mix of objects. So every row or every feature can be a different thing. Again, that can be quite powerful and quite dangerous, especially if you're coming from a conventional background and you expect it to be all the same. So just be aware of that. I'll try not to, I'll keep things simple here. Okay, so again, we'll start very simple. We'll be constructing Geo Series by hand, but using the Shapely tool that reads from well-known text strings, just to give you a feel for where well-known text may come in. So let's see, where was I? Oh, I should say one more thing, not that it matters a whole lot, but you'll see that in the first cell of the notebook there's a data path line, and that refers to that data subfolder that has some shape files that will, and geopackage files that we'll use, plus other things. Again, if everything works, you don't need to worry about it, but as you use this locally in your own computer in the future, just be aware of that. Okay, so we'll run this. It runs. What we're doing here is we're passing the rawest form of data. You will never do this in practice. This would be an awful way of converting data. But we're taking the well-known text string representation and creating a list that using the loads function from Shapely and creating a list out of that and passing it to the Geo Series constructor. And now we have a Geo Series with three geometries. They're all points. Again, you would almost never, except in rare, very idiosyncratic cases, would you pass actual strings in well-known text. Here, the next one is a case that's much more realistic, and you actually may use it, where you start out with the individual values of your lat long, if you will, and that's what I try to mimic here, and you use a function, point, or a constructor from the Shapely library. So you can totally imagine reading like a CSV with lat long and using something like this, where you take the lat long columns and use the point function. Ta-da, you have a Geo Series with geometry types. And okay. Like I said, a Geo Series or GeoPandas can store a CRS implicitly that is implicitly associated with the geometry column. It's just made of data. You do want to use it. You want to keep it accurate. It's not totally needed. It's only needed so that you know what you're doing, I guess, but also so you can do transformations, reprojections accurately. In this case, because I just created the Geo Series, it had no idea what projection it was, so I assigned it. If you're not familiar, this is one of several methods or ways to assign it a CRS. If you're not familiar with EPSG codes, you should. They become a de facto standard for passing codes that define a projection. And I can answer questions about that later. Okay. So now that we have a data set, a Geo Series, we can plot it. I need to be diligent about running every cell. Keep forgetting. Okay, that ran. So that's our Geo Series, just 3 artificial points. And then I used matplotlib machinery to tweak it, to tweak the X limit and Y limit. And that lingo, if you're not familiar with matplotlib and you are with MATLAB, that syntax should be very familiar. And I specified the marker type, the color, the marker size, and there may be something funky going on with marker size here that may have to do with matplotlib 1.5 versus 2, and the figure size. Okay, so we'll get a tiny bit, we'll start getting fancier here and build. Geo Series typically are not that useful in and of themselves, but they're a component that you need to be aware of so that you can fully take advantage of that capabilities. But really, you almost always want the geometry plus some attributes. In other words, complete features. So we'll create a very simple Geo Data Frame by building on that Geo Series. You can see that the geometry here is the same as before, and now we'll be adding one attribute, name. And this is a common way of storing, of pre-processing or storing data before you pass it to a GeoPandas Geo Data Frame. But they're Geo Data Frames, just like Pandas. Data frames can read from multiple formats and multiple structures. We'll reuse the approach we just saw. I think this listing. This is a list of points, except here we get fancier and we use what's called list comprehension in Python. It's a compact way of defining a simple for loop, basically. Won't get into the details of what zip is doing, but trust me, this format is something you will use. This construct here. Okay, we'll run it, and now we have a Geo Series of 3 points. no, I'm sorry, it's a list of shapely points. And now I'll turn it into a Geo Series where the index is the name. So before, the index was auto-assigned. I see a question there, sorry.
Can you briefly explain what that, I guess it was line 10, what that format?
This one?
Yeah, how you...
Oh, sorry, I forget that. Oh, you are seeing my cursor. Okay,
if that's good.
Someone stop me if I go into all details. There are two things here that may be complex if you're not familiar with Python. The first one is the list comprehension syntax. Think of this as a for loop where the for part is from here to here. Ignore the zip part for a second. Just assume you know what that is. And then the inside of the loop would be this. You're constructing a list element by element by stepping through this loop and then adding elements like this point x, y, to the list, appending elements like that. It's a syntax that might be unique to Python. It takes a bit of getting used to, but once you do, if you don't abuse it, especially if you don't make it complex, it's really intuitive. It makes for cleaner reading of code. So that's the first part, list comprehension. The second part is the zip. We're taking this dictionary here, taking basically the first value by zipping lon and lat. We're going to be stepping through these elements, the first one of this list here, records. This is the first one of name, first one of lat, first one of lon. So we're going to take the for that list, in that order, take the lon and lat and create what's called a tuple, well, a list of two elements. The first two elements, basically, or the first element of lat and lon become a pair. And then you pass that to point. And then the second one and the third one.
Thank you.
Okay. I can answer more questions about that later if anyone has questions. Okay, so that was a list of points, and now we turned it into Geo Series. I think I ran this already, but just in case. Okay, now we'll build up to Geo Data Frames. Like I said, a Geo Data Frame can be described as a feature collection where each row is a feature, and there's a geometry column, and all the other attributes are the properties. Be aware that GeoPandas doesn't restrict, unlike a shapefile, for example. GeoPandas or GeoData frames don't actually restrict you to have a single geometry type column. You can have as many as you want. Only one of them can be defined as the active geometry for the GeoData frame at any given time. We won't get into that here, but just be aware of that as you start using GeoPandas. Okay, so we have the data. Okay, the dictionary called data out there, and we'll use a pandas. We'll turn that into a pandas data frame with this simple approach, but as simple as it gets. So here's a pandas data frame with those three attributes. Pretty easy. Now we'll use that data frame and the approach we just saw for constructing a Geo Series or the list of geometries to create a Geo Data Frame. So you can see the same approach we just saw before, a list of points with the same syntax, and now a Geo Data Frame where we're passing the data frame to get all attributes, and the geometry comes from that list. So hopefully this makes it all worth it, all the tedious first steps. Nothing new here. This is exactly the same data set we were seeing before, except there's a new attribute. We'll still visualize it just because seeing things is fun. So it's still the boring data set of 3 points. I mixed it up a little bit by changing the figure size and using a green color. But just notice that now we're using the plot method on a geodata frame. Before, it was the plot method on a Geo Series. It's for all practical purposes it's the same, but there are differences. There are subtle differences. Okay, so we'll start building up to more real data. It may be disappointing in that you'll find it kind of head-scratching, but trust me, it's real data, sort of. Okay, so I used the GeoPandas read file. method, which is a workhorse to read shapefile, geopackages, etc. It leverages the fantastic Fiona package, open source Python, which in turn leverages OGR. It simplifies access to this OGR tool, which is used by everyone, including Esri. But if you use it in Python, it's sort of low level and hard to code and just awfully long code. When you use it, Fiona makes that a lot simpler and more compact. Okay, so we now have a geodata frame. I'm going to show you the first few rows. Head is a common Pandas geodata frame, or Pandas data frame construct to show you just a subset of values. This data set is so small that it may actually be showing you all data sets, all features. Okay, I'll also show you that the CRS was read. This shapefile had a projection file, and it was read and added to the metadata. Okay, so we'll now plot it. Again, here the emphasis is on data exploration. So when you're doing that, the emphasis is I want to see that darn plot easily and quickly. I don't want to have to compose 5 or 10 different lines just to get set to create my axis and then get set to actually see something. I don't care how big it is. I don't care about fonts. I just want to see something quickly because my creative juices are flowing. So you see that I have the Oceans geodata frame, use the plot method. I happen to specify this arguments that I pass are totally optional. You could have gotten, in fact, let's do that. I only chose them so that the result would be prettier, but here we go. Can't get any easier than that. A plot method, and you get a plot. Now, it's kind of ugly. It's probably a lot better in Matplotlib 2.0, but you can make it a lot more user-friendly and helpful very easily. So what this is, let's see. Well, maybe I'll explain it very briefly. Even though this is called oceans, these are not actually the ocean polygons or boundaries. What the boundaries that you see here, especially the ones on the left, I guess, but the ones that run vertically are not the coast. They're really more like the middle of continents. And I'll explain why that is later. This is kind of not fake, but a particular data set that Don and I developed for a very specific application, marine application that I'll mention later. But I'm using it here because it's so simple. It's just a few polygons and it's global. It happens to store both polygons and multi-polygons. So here's where you can leverage the geodata frame built-in functions to give you the geometric type of each row. You can see here that some are polygons and some are multi-polygons. And then more, you can, to illustrate more of the, where did it go? Terrific built-in functionality in geodata frames. You can use the geometry. So you have your Oceans geodata frame, apply the geometry module probably, and then you have an area property. So you can get the area of all these polygons in the projection that you're using. In this case, because it's lat long, the area will be in square degrees, which is kind of useless for most purposes. But still, you get the point that you can get at the area very easily. You can also create or extract bounding boxes very easily. It's just a method. Just like geometry.area, this is geometry.bounds. And that could get more useful. You can build envelopes on this. And the envelope itself has a plot method. So now we go from the actual polygons, those blobs, into bounding boxes. Now there are cases where you have polygons and bounding boxes. You want bounding boxes for all sorts of reasons. Now this bounding boxes can get a little tricky because some of these span the whole world. Don't worry too much about that, but I'll explain why that is. That's because there are some oceans or ocean features here that in reality are multi-polygons, and they are, because we're cutting the world at -180 and 180, the Pacific Ocean is split into 2 pieces here. So it's a multi-polygon, and when you take the bounding box of this multi-polygon, it's going to span the whole range of longitudes. And because you shouldn't believe what people say, you should just see it, we're going to see it in action and apply Pandas filtering capabilities. Here's Pandas syntax. We take Oceans Geo Data Frame, select the Oceans column, and only pull out the North Pacific Ocean, where the attribute Oceans is the North Pacific Ocean, and then plot it. And I wanted to plot it with a certain size, and to use the same y-axis limit as a range as what we saw above here, just for comparison, just so that you have a sense that this is the polygon that represents the North Pacific Ocean. It has these two pieces or blobs, and that's why a bounding box would end up crossing the whole world. But hopefully, on the way to this, you see this great Pandas data frame syntax for filtering on the fly. And here we're doing both filtering on the fly based on an attribute and then plotting. All disposable. You're not creating a new shapefile. You're just applying a live filter so that you can do a plot, and that's it. Okay, we'll get to more real data now. GeoPandas, like many other data packages, comes with a sample data set for test, to run tests, and in some cases it's of real use. It comes with Natural Earth, which is a public domain data set that can be pretty cool for cartographic purposes. I think it's a subset of that. So you can load this with the GeoPandas datasets module, get the path and pass it to read file, just like we were doing before. So we'll use this one called Natural Earth Low Resolution, which is basically countries. Show the first two records, and you can see that it has a population estimate from who knows what year, continent, a name of the country, a standard ISO code for the country, and then the geometry. You can also see that I don't even know what format this is coming in from. This is stored in probably shapefile, but to tell you the truth, I don't know, and it doesn't matter in this context. The CRS was read, and now we can do a simple plot. And again, you can see that it's just a base map, if you will, for countries. But we'll use it as more than a base map. We can use it to bring context to that weird oceans data set that I was presenting by combining, again, data exploration. And so you want simple and compact ways of doing plots. In this case, we have our, let's start in the inside. We've done this before, oceans.plot and then some parameters. But now we put it on the inside of another plot method of a geodata frame, and set an axis, and then tweak the styles. And what we end up getting is an overlay, or a simple plot with two polygonal data sets being displayed in what I think is a very compact syntax. So again, think data exploration here. You got creative juices flowing, you want to see the relationships, you want to picture this, you don't want to spend your time laying out the axis, etc. So you can do this quickly and get overlays. And now, of course, you can use Matplotlib machinery to finesse these plots. And this is what this is. It's the same plot, really, except instead of using the plot method in a geodata frame, we turn to Matplotlib to enhance those plot capabilities. I won't go into details there unless people have questions, but I'm doing things like setting the Y limit to a specific range, adding a title, finessing the styles, and removing the axis labels, because we know we don't need it. Okay, we're going to get to fancier things now, including reading from PostGIS as an illustration. PostGIS being a relational database, the geospatial extension of a relational database. We load those libraries, JSON and PsychoPG2, and hopefully that'll run. What this is doing, what that step did, is it read a database connection credentials file. You should have a copy of it. In fact, the fact that it ran for me means that it'll run for you. What I did is not the best practice for security, but it's on GitHub. It got pulled into your repo or your clone on Jupyter Hub, and it gets read here. It turns into a dictionary, and then we pass it to PsychoPG2 to connect to the database. The connection is set, and here's a taste of what it looks like, where I've hidden the password on the user so that this public notebook doesn't expose that information out there. So we now have a connection to a PostgreSQL database that happens to be sitting on an Amazon Cloud instance, though that's completely irrelevant. If you are a PostgreSQL pro, you have PostgreSQL on your laptop or on your server when you go home, you could go tweak that DB.json to your own connection and reuse it any way you want. In this case, it just happens to be on Amazon. Okay, so we have the connection. Now we're going to do real things. Read this new data set called world seas. And unfortunately, you have to know bare minimum of a SQL syntax to use this. But if you're interacting with PostGIS, you probably know a little bit of SQL. In this case, this is the simplest. Just basically specifying the table or the geospatial data set is called world seas, and I want everything. I want all the attributes and no filtering. You do have to know, unfortunately, in GeoPandas, the name of the geometry column and pass it. It's not able to guess it right now. Hopefully that'll change in the near future, and you can contribute that. There's another thing that I find unfortunate, that you have to pass it the CRS. I think it should be able to read it from PostGIS, but the capability is not there. You can click on that. If you're a Python developer, click on that link, go to GeoPandas issues, and contribute that enhancement yourself. Thank you. Okay, so we're reading now. You can see that it's taking a little bit of time because it's actually reading that entire data set. I can't remember, so whatever, from the cloud, literally. From a cloud to a cloud, I guess. It's done. And I'm not going to reuse this PostGIS connection again, so be a good citizen and close the connection. And I will look at the Geo Data Frame, just like we have done before. We used head. In this case, it has more attributes. And by the way, this data set, I forgot to put a link to it, to where it comes from, but it's a data set, an official data set, shared by a group in Belgium, I think, from the IOC, some international body. And you'll see what it represents. It represents seas, things that are much more specific than Pacific, things like the Caribbean or the Salish Sea, maybe, although I don't think it's there. Certainly Mediterranean, the Adriatic, and so on, Arctic. And you have official codes. I think we added, I forget if it was Don and I that added this oceans attribute. Okay, we did, to make it more useful. And we also added this attribute, but it doesn't matter. Okay, so now we can use it to do more advanced and fun plotting. But we're using pretty much what we've learned already, except now that we're dealing with more interesting data, we'll introduce the ability to use a categorical plot on a GeoPandas Geodata Frame. So the same, we have a Geodata Frame plot method. Now we'll pick which column to plot on, if you will, and whether we'll treat it as a categorical column so that each color is distinct, and whether a legend will be popped up by default. And then we tweak the figure size. So ta-da, that's, again, think data exploration, not publishing your beautiful 6x6 map. That's quite a bit of work, actually, to, if you ask me. I mean, little work to do quite a bit of a map as you do in exploration. The legend popped up by default. There's a slight limitation right now that apparently the plot method in Geodata Frames doesn't allow you to control where to put that legend. So hopefully it'll be fixed soon. So in other words, I would put it down here out of the way. But so be it. Okay, there are resources here that you can find a lot more capabilities. And now we'll start combining more of what we've learned. We learned about filtering based on attributes. We've also learned that there's this area property that you can use for each polygon, each geometry. So what we're doing here is we're going to pull out all the seas that have an area, a polygon area in square degrees that is less than 10,000 or 1,000. So we're going to pull out all these seas whose oceans attribute or column is North Atlantic Ocean, and the area is less than 1,000 square degrees. And then we're going to plot it. And in addition to plotting it, do a little extra finessing. What this does here is define an optimized set of boundaries based on the envelope, basically, or the bounding box. And we are reusing that approach of having an overlay to provide essentially a base map. We're using the world Geo Data Frame with a light gray face color or polygon color so that you have this reference of the world that's not obtrusive. And you can see that each polygon here is a sea. Like Gulf of Mexico, etc. Oh, I guess, well, you could see where these seas are, or what level of resolution. So that's, I don't know, if you ask me, that's a lot of, we did a lot of processing in very simple steps. This attribute and geometric filtering, and then simple plotting. Okay, if you want, I'll run this, but if you, as you're exploring, you hit on something that you think you'll reuse, so you can use GeoPandas capabilities to save it to a file. So I'll save this to a shape file, and it'll get saved on Jupyter Hub, I guess, and I won't look at it again, but just to illustrate how easy it is to save your work. Okay, so the next and final in this intro notebook, the final extra or illustration will take us in a different direction. Instead of looking into relational databases, we'll look at web services and standard access to data online via standardized web services. In this case, it's an Open Geospatial Consortium web feature service that, in order to make it more predictable, it's one that Don and I manage by this organization called Nanus. Okay, so we define two libraries, request that handles generically web services and web access. We define the endpoint, the web endpoint, and then pass parameters. Don't worry about the details of this because the intent here is not to teach you everything you need to know about WFS. So we define the service type, version, what request type we want, and basically the layer. And the output format is JSON or GeoJSON, because once we get that, we can do what we've learned with JSON. So I'm going to run that, and just be aware that I think Amanda mentioned GeoServer yesterday, and I think she was actually referring to this Nanus GeoServer instance. So what we've done is with the advanced knowledge of where that is, the endpoint, and the layer name, we've requested a particular layer that I happen to know is a point layer, but it doesn't really matter. And then you would use this convenient GeoJSON library to, what you get back is actually a GeoJSON string, an ASCII string, basically. The GeoJSON library takes that string, converts it into an object that is GeoJSON-like, like a dictionary. So now we're ready. We're ready to apply what we've learned. I'm going to use some printouts just to, so you can examine what this looks like internally. It's a GeoJSON feature collection, which is essentially like a dictionary that has these 4 keys. One of them is features, so a list of features. And if you use the geo interface method that I mentioned, you can get at the length very easily. So it has 544 objects, or geometric objects, or features rather. Now I'm going to use the from features method or constructor from Geo Data Frame to turn that into a Geo Data Frame very easily. Ta-da! We got a Geo Data Frame, and now that we have a Geo Data Frame, we can do what we've been doing, plot it in a convenient way. We're reusing the world Geo Data Frame as a base map, and then the points that you're seeing are the data set I just downloaded, and we all downloaded on the fly from a web service. And just to wrap that up, this is what one of those features looks like. If you're curious, we're not leveraging any of it.